Session 1 on work power energy, we covered some basic calculations related to work, how to calculate work in various situations, work done by a constant force, work done by a force varying in magnitude, varying in direction, varying both in magnitude and direction, right? These were some of the things that we got acclimatized to in our last session on work power energy. I'm assuming that you have read enough familiarity by going through that stuff over and again at home, and that you are already comfortable with all of it, right? Can I assume that? Right. I mean, there was, you were so mellowed when you had to say a yes. I would have liked you to all resonate and say yes in tandem. But then, you know, I could see that you were very skeptical about committing to say, yeah, we did it. Have you done that? Yes, sir. All right. So that gives me enough encouragement to get on to some more of related stuff on work power energy. Now, what I want to discuss at this point is the concept of a field, a force field. So, a force field. When I talk of a field, I'm talking of a certain region of space. When I talk of a force field, then I'm talking of a certain region of space such that at every point of that region, I could associate a force vector which is the force acting on a test particle when placed at that point. Which means this is the certain region of space. At every point of this region, let's say this is a certain point. If a test particle is placed at this point, then there is a predetermined force F1 that will act on that particle when placed at this point. When the particle passes through this point, the force acting on the particle will be F2. Let's say when the particle passes through this point, the force acting on the particle will be F3, and so on and so forth. So in this region, we have knowledge of these force vectors at each and every point. This is said to be a force field. With every point, I could associate a vector, a force vector, which will tell me the force acting on a test particle when it's placed at that point or it passes through that point. You know, there could be a particle in this region, and on its passage through this point, we know for sure when it's passed through this point, it must have experienced a force F1 like this. Now, it does not matter how the particle passed through this point. It might have passed through this point this way, then also the force experience will be this. It may have passed through the point this way, then also the force experience would be this. It does not matter. All that is important is on its passage through this point, or when placed at this point, the particle will experience, the test particle will experience a force given by F1. We then seem to be having complete knowledge of the vector force field for this region. You know, it might have been tabulated or might have been provided to us in some form or the other. With given a point, I would know the force experienced by a test particle at that point, whether placed at that point or passing through that point in any manner. Right? So that's a force field. That's a force field. Yeah. At every point of this region, it will experience a force. At every point, it will experience some force or the other, and we have knowledge of that. We have knowledge of the force that a test particle would have experienced at every point of this region. Right? Now, in a very general sense, so that's a force field. That's a force field. A vector representation of a region in terms of the force a test particle would experience at every point of that region. That's the force field. Clear? Now, in a force field, suppose, you know, a test particle undergoes a certain trajectory in a certain force field from a point A to a point B. From a point A to a point B, a particle undergoes a certain trajectory. Now, when it undergoes this trajectory, it's not necessary that the particle underwent this trajectory only at the mercy of the forces of the field. It might have been acted upon by other forces, etc., which may have caused this resulting trajectory. But does not matter. Does not matter. When it comes to work done by the forces of the field, then I don't care what other forces are acting. I am only looking at the force at every point because of the field and calculating the work done commensurate. Which means, let's say if this was a trajectory owing to a combination of factors, couldn't care less, and I want to calculate the work done by the forces of the field when the particle migrates from A to B. Well, when the particle goes from A to B, what varies is the position vector of the particle. P, let's say, is a certain instance of the particle where the position vector is R. Right? So when I say that I have knowledge of the force field, when I say I have knowledge of the force field, all that I am implying is that the force acting on the particle as a function of R, position vector, supply the value of the position vector, you would know the force vector acting on the particle. So force, a function of the position vector R. For different R's, in general, it could be different. It could also be a constant force field, does not matter, but we'll generalize things. Now, at this point P, for example, when the particle is at a point P with position vector R, say the force acting on the particle is F at R. This is F at R. Clear? This is F at R. F at the point with position vector R. Now, to go to its mathematically neighboring point on the curve, it must undergo a change in R. The change in R is dr, infinitesimally small change in R, which is also along the tangent to the curve at P, right? The dr, the change in R is this. To go to its neighboring point, what's the work done by this force? F dot dr. The force at R dot dr is the small amount of work done by the forces of the field, in its migration from P to its neighboring point, mathematically neighboring point. All right. Now, does not matter. I don't care. I mean, the work done by this force will be this only. Whether there are other forces or not, it does not matter. This, all that I am trying to calculate is the work done by the forces of the field. And it does not care about, as long as you have knowledge of the resulting trajectory, the other forces acting will also do work, but that would be independent of the work done by the forces of this field. Right? They will not interfere with each other's action. The resulting trajectory, of course, would be an outcome of the action of all forces acting on the particle, but the work done by this force will not require, or to calculate the work done by this force, it will not require intervention of other forces. If I have knowledge of the trajectory, I can calculate the work done by every single force acting on the particle. At this point of time, I am only modestly trying to compute the work done by the forces of the field, the forces related to the field, right? So I have knowledge of this F as a function of R. So this is the work done by the force of the field. When, see, loosely I would say work done by the field. When I say work done by the field, I would actually mean work done by the forces of the field, right? So work done by the field in brief. So the work done by the field to go from P to its neighboring point is going to be this, right? Say R of A is RA, position vector of A. Position vector of B, say, is RB. Then the work done, total amount of work done, would be obtained by doing a F dot dr, F dot dr, F dot dr for every single point of this trajectory, where in a very general sense, F would be different for different R's, right? And then I do a summation. The summation of all of this is like this operator adds up all the F dot dr's for us, where R runs from R of A to R of B. That's the total amount of work done in going from A to B. Total amount of work done in going from A to B along this trajectory, right? No, when did I say the force is constant? When did I say it's a function of r? I never said it's constant. In general, as a special case it could be constant, but in general f would be different for different r's, right? Now in a general sense, this work done from A to B will depend on the path actuals. What the exact trajectory is will determine the work done from A to B in a very general sense. In a large number of force fields, in general, the work done will depend on the exact trajectory of the particle. But then there are some special force fields. That the nature has to offer. These force fields are such that if I know an initial point and I know a final point, then the work done by the forces of the field from the initial point to the final point does not depend on what the exact trajectory might have been, does not depend on the path actuals, right? So there are certain special force fields where this work done from A to B, is path independent. The work done by the forces of the field in certain force fields is path independent. That means whether you go from A to B via London or you go from A to B via Patna, the work done by the forces of the field will be the same. Okay. That means the calculation of this integral will give you the same value irrespective of the path actuals between A and B. Such fields that characterize path independent work done, such force fields are called conservative force fields. Sometimes we'll simply say a conservative force field. Work done from A to B does not depend on what exactly the path might have been between A and B. Such is the character of a conservative force field. Clear? Path independent work done. Now, can I wipe this off? So, let's move to a conservative force field in general. Let's move to a conservative force field where again I have a region where at every point of that region what the force a test particle experiences is known to us, and the work done between any 2 points does not depend on the path of the test particle between those 2 points. It's going to be the same, right? We'll focus on conservative fields now. So, say in a conservative field, I have 2 points A and B. Okay, and the force at any point as a function of the position vector of that point is known to us. The force vector acting on the particle at any r is known to us, say. Clear? And in a very regulation procedure, we do a f dot dr for every point between A and B, and I'm able to calculate the work done from A to B along this trajectory, say. F dot dr for every single point. R runs from Ra to Rb, gives me the work done by the forces of the field, or work done by the field, from A to B. Clear? Yes or no? Now along this trajectory, the work done, let's say, is W from A to B. Let me call it W units. W joules of work done is W units of work is done from A to B. W units of work is done from A to B along this trajectory by the field. Which is like, if there was a certain point P, if F was like this, then in going from A to B, I do a F dot dr, and I calculate this work done, right? When I go from A to B along this trajectory. In contrast, if I had to transport the particle from B to A, so W units of work was done. W units of work was done in transporting the particle from A to B under the influence of the field. W joules of work was done. And now along the same trajectory, it'll be difficult for me to draw the same trajectory, but I'll try and do that. The same trajectory, I'm just redrawing that. Same trajectory, but now I choose to transport the particle from B to A. Right? So it passes through each such point P. Now, when it was going from A to B through this certain point P, then the force acting on the particle was F like this. But in its motion from B to A, when it passes through the point P, what would be the force vector acting on the particle? Same. The force field does not identify the direction of motion of the particle. It does not know anything about the particle. It just understands that when the particle passes that point, it has to exert on the test particle the same force F, irrespective of the state of motion of the particle. Right? So it experiences a force F like this, let's say, right? Now this was theta, so the work done was F into dr into cos theta when it went from here to here. But when it's going this way, see, right, instead of theta you have the displacements like this. The displacements are like this, right? And this angle is pi minus theta, right? So the work done when I am going from B to A through a certain point P, instead of being F into dr into cos theta, the work done is F into dr into cos pi minus theta is the work done in this case. Right? Which is like minus F into dr into cos theta is the work done in this case. That means the work done in this case, let's say dw1, is negative of the work done in this case. Right? For every equivalent displacement in the opposite direction, the work done in this case would be negative of the work done in this case. What do you say? So if the work done from A to B was W units, then along the same trajectory, the work done from B to A must have been minus W units. Right? Therefore, if the work done from A to B along this trajectory was W units, then from B to A along the same trajectory, the work done must have been minus W units, right? So the work done from B to A is minus W joules. Minus W joules must have been the work done from B to A. What do you say? Right. Now, can I wipe this off? I have not yet used the fact that it's a conservative field. In any field, in any force field, that's not acting crazy. If the work done from A to B along a certain trajectory is W, then along the same trajectory from B to A is minus W. See, have I at all used the fact till this point that the field is conservative? No. But what I'm going to say subsequently would be more about the conservative field, right? This in general for all fields, right? Now, can I wipe this off? Wait. Gravitational force field is a conservative field. Spring force will be a conservative force. Magnetic fields, electric fields, they are all conservative fields. Fields produced by charges at rest, magnetic fields, they are all conservative fields. Gravitational force field, most commonly, that's a conservative field, right? Now, one thing is evident. If the work done from A to B is W units, then the work done from B to A will be minus W along the same trajectory. If I go this way, the work done is W, but if I went from B to A, the work done would be minus W. Right? Clear? Now, if this field was conservative, and if the work done from B to A along this trajectory was minus W, then what would be the work done from B to A along this trajectory? Minus W. It still be minus W. Right. In a conservative field, if the work done this way was W, and this way must have been minus W irrespective of the field, then the work done this way along any other trajectory from B to A will still be minus W. If I have found one path between B and A that has resulted in minus W joules of work done, then any other path between B and A would result in the same amount of work done. That's the trait of a conservative field. That's the basic trait of a conservative field. Yes or no?
Yes, sir.
Right. Now, therefore, if I had to imagine a test particle in a conservative field, being transported along a closed loop, right? This is ABA, which is a closed loop. A to B to A is a closed loop, yes or no? This is a closed loop. If I had to imagine a particle being transported from A to B and back to A in a closed path, in a closed loop, then what's the total amount of work done? 0. W plus minus W. The total work done in a closed path A to B to A must have been W plus minus W, which must have been 0. The work done in a closed path, in a conservative field will always be 0,
So we can look at like this. It is not undergoing any displacement.
No. But in a non-conservative field, it comes back to A. Then also there is no displacement. Does it mean there is no work done? What he's saying is, its work done is not F dot net displacement. It's F dot dr. Doesn't mean that if there is no net displacement, work done will be 0. See, for example, okay, think of it like this. Say kinetic friction between these two surfaces is, this body is moving to the right, is being pulled to the right with a certain force, and there is kinetic friction Fk that will act leftwards, right? Now it's taken S units to the right. What's the work done by kinetic friction? Minus Fk into S, right? Work done by kinetic friction would be minus Fk into S, right? Now, bring it back to this point. The direction of frictional force now would be Fk like this. Work done by frictional force in moving it again back to this point would be Fk into minus S once again, because now S is this way. So minus Fk into S. So is the work done 0? Even though the net displacement is 0. The particle has gone to this point and come back to this point, but the work done by friction is not 0. Have I confused you? So it doesn't mean that if the net displacement is 0, the work done by the field must be 0. No. That can happen only in a conservative field. That's why the conservative field is special. It will not happen in all fields, it will happen in conservative fields. That if there is no net displacement, that means you must have undergone a closed loop to come back to the same point. The work done ought to have been 0 then. Right? So far so good, right? I hope all of you understood what I said here, right? Now, do you understand what potential energy is? What is potential energy? What is potential energy? Due to its? By virtue of its position. Any other answers? Same? What's the difference? See, whatever you people have said, can your definition be used to calculate potential energy? Energy by means of position, all right, accepted for a moment. If it's energy by means of position, by virtue of position, as some of you said, how do you calculate the potential energy using this? Huh? Huh? Sasure. Nahi, sorry. Let's change in work done. Huh? Work done? No, potential energy is not just about gravitational fields. It could be in electric fields, it could be in, huh? See, all that they have taught to you about potential energies from the time you were toddlers, you still are, is junk, crap, irrelevant and shit. If a definition can't be used to arrive at numbers, then that's no definition. They made a fool out of you. I was just hoping that your teachers in 11, 12 in school will do justice, will help you migrate from the charge test particle. No, you're not wrong, but that's adapted from something more fundamental. I'm not saying you're wrong, but that's adapted from something more fundamental. I don't want to deviate from fundamentals right now. I want to, go ground up. That's a little hazy, but then you are converging. Yes, Ayush, na? Yes, Ayush. Is what? No, coming closer, you're getting a little better in your description. Let me first of all tell you that potential, when we talk of potential energy of a particle in a certain region, we are talking of potential energy of a particle in a certain force field, but not all kinds of force fields. Potential energies are defined only for conservative fields. Potential energies are not defined for non-conservative fields. Potential energies are defined only for conservative fields. Only for conservative fields. 1. If they are defined for conservative fields, what should they be then? That's the question. In a conservative field, if a particle is known to be at a certain spot, is known to be at a certain position, what is its potential energy? That's the question we must address. At a certain point, in a region of a conservative field, if a particle is present, what should its potential energy be? That's the question to be addressed. There is no answer to this. There is nothing like potential energy of a particle at a point. It's a meaningless proposition. No one ever defined this. Okay? But what is important is, in a conservative field, so potential energy, the domain is about a conservative field, right? Now, if I have 2 points in a conservative field, A and B, any 2 points in a conservative field, say A and B. Clear? Then there is a certain amount of work that is done when the particle goes from A to B. There is a certain amount of work that is done by forces of the field when the particle is transported from A to B. And does this amount of work depend on the trajectory of the particle? No, it's path independent. It's path independent. Clear? Now, so irrespective of what the path is, the amount of work done by the forces of the field when transported from A to B will still be W. Will still be W. Now we define not the potential energy at A or B, we define what's called the difference in potential energies between A and B. Potential energy at A is not defined, potential energy at B is not defined, but the difference in potential energies is defined. We define the difference in potential energies between A and B, delta U. Delta U, delta means change. Change in U. U is the potential energy. The change in potential energy between A and B the change in potential energy between A and B is defined as negative of the work done from A to B. Is defined, this is the definition of not the potential energy but the change in potential energy when the particle goes from A to B. When the particle has migrated from A to B, if W is the amount of work done by the forces of the field, then minus W is defined as the difference in potential energies between A and B. That means this is final potential energy minus initial potential energy, UB minus UA. Negative of the work done from A to B is final potential energy minus initial potential energy. That's the definition. What's your name? Why not Rashi? Sorry, slip of tongue. Right? So that's how work done F dot S. That's the way they defined work done on this planet, because certain things matched with it later on. So they said, let's all put it in a template. All right. Let's just put it in a template. So when I'm defining, no definition will be subject to discussion. A definition is a definition is a definition, right? That's how. In some other planet, they could have redefined potential energies as W. That's fine. Although you'll see some rationale in it down the line based on how physics evolved later on, right? But then for the time being, let's simply look at it as a definition. We'll see rationale in it once we learn little more, but at this point of time, let's be happy with this being the definition. Clear? U is potential energy at B. UA is the potential energy at A. Whatever be it, we don't know the values, but we know only the difference in the values. So keep the UAs, UBs in black box. We don't know about them, but we know about UB minus UA. That's defined as minus W. Potential energy at B minus potential energy at A is defined as minus W. Work done from A to B is W units.
So if the particle is moving from like A to any other point C, then the potential energy at A will be constant. Or it will change.
First of all, did I tell you there is anything about the potential energy at any point? I told you. Right now, don't get so, stuck to this idea about potential energy at a point. Don't feel lost with this. Let me develop it a little more. You'll realize that it does not matter what UA is, which is what I'm going to share with you in a little while, right? So, in brief, what's defined is UB minus UA, which is negative of the work done when the particle is transported from A to B along any trajectory. And by the way, whether this trajectory or this trajectory or this trajectory or this trajectory, the work done will still be W units. And negative of this will be UB minus UA. Right? See, in a non-conservative field, this couldn't have been defined this way. Why? Because this W would be path dependent. That means UB minus UA will depend on the path. Potential difference between 2 points will depend on the path. That's not what we want. That's why the whole concept is not even defined for non-conservative fields. It's defined only for conservative fields, right? Now, can I wipe this off? Extend this idea a little more, right? So fundamentally, all that is defined is difference in potential energies, not potential energy, right? Now, given this, let's concretize things a little more on potential energy. Say there is a point A in a conservative field. Let's say there is a point A in a conservative field, right? And there are other points, say A1, A2. I mean, this entire region is, but let me examine a set of points, A1, A2, A3, A4, etc., some other points, right? Say, with the help of elaborate computations, I calculate the work done by the forces of the field when the particle is transported from A to A1. And since it's path independent, my choice of path should be convenient. Something that will make my calculation of F dot dRs easier. Right? Because it's path independent, why not choose a path that's easiest to deal with? But forget about all that for the time being. Let's say I do a calculation of the work done from A to A1, and let's say 20 joules of work is done by the forces of the field from A to A1. Work done is 20 joules, say W1 is the work done from A to A1. That means if the potential energy at A1 was UA1 and A was UA, then UA1 minus UA must have been minus 20, right? Suppose the work done from A to A2 was minus 10 joules. then what it means is UA2 minus UA must have been 10 joules minus W2. Right? Say the work done from A to A3 was W3 and was minus 5 joules. Then what it means is UA3 minus UA is 5 joules, and so on and so forth. Say the work done from A to A4 was W4, which is minus 30 joules. Then UA4 minus UA must have been 30 joules. All right. Now, and this I can do for all points A1, A2, A3, A4, A5, A6, AN, covering all points in that region. Right? But then, there is no way I can calculate UA or UA1. There is no way I can calculate UA2, UA3, UA4, UAN. None of this could be calculated. Right? And in fact, it does not even matter what values exist for UA, UA1, UA2, UA3, UA4, UAN. It does not even matter. Why? Because all that is important is, let's say, the work done from A to A1, that means all that is important is UA1 minus UA. All that is important is UA2 minus UA. All that is important is UA3 minus UA. UA, UA1, UA2, UA3, their absolute values are inconsequential, You know what I'm saying? Now, if the absolute values are inconsequential, you know the absolute values of UA, UA1, UA2, UA3, if they don't matter at all in terms of the physics of the situation. See, the physics is about the difference in the U's. The physics is not about UA or UA1 or UA2 or UA3. The physics is about the difference, right? So then, a pragmatic approach follows. What we could then decide is that one of these points, say A, A1, A2, A3, A4, any one of these points, be chosen as a reference point. We could choose one of these points as a reference point. All right. Say I choose A as a reference point. Once I choose A as a reference point, then it's my prerogative. It's my prerogative to assign a certain value to UA, A value UA equal to minus 1 could be assigned. I could say, all right, UA will be minus 1. Or I could say UA would be root 2. Or I could say UA would be Boltzmann's constant. Or I could say UA would be 1 mole. UA would be 3.6141 into 10 to the power minus 16 divided by 100.16. Any value of UA could be assigned, right? But then, why make it clumsy? Assign a convenient value to UA if you have the choice and if it does not matter what UA is, right? Why not? Why not assign? Why not bring convenience for yourself, right? So I'll say, all right, A will be my reference point and I will choose UA as 0. I will choose UA as 0 because it does not matter what UA is. I will choose UA as 0. Right? Now, if I choose UA as 0, for example, then very evidently UA1 will become minus 20. So UA1 will become minus 20. UA2 will become 5. UA2 will become 5. UA3, I'm sorry, UA2 will become 10. UA3 will become 5. UA4 will become 30. UA4 will become 30. And so on and so forth. So then, loosely speaking, I could have said, well, all right, the potential energy at A is 0 joules. The potential energy at A1 is minus 20. Potential energy at A2 for the test particle is 10. At A3 it's 5. At A4 it's 30, and so on and so forth. Right? If I choose a reference point and assign a specific value of U to that reference point, then very readily I could assign specific numbers, scalars, to all other points in that region of the field. Right? Now, someone may not be happy with UA equal to 0. Right? See, Shashi is not happy with UA equal to 0. So he says, damn thing, I'll have UA equal to 5. Finish. Take it. So he says UA equal to 5. Now once UA is 5, all the UA1, UA2, UA3, UA4 increase by 5 units. All of them increase by 5 units. Yes or no? That means this will become minus 15, this will become 15, this will become 10, this will become 35, and so on and so forth. Right? But what happens to the difference? It remains the same. Right? Because everything has increased by 5 units. This has increased by 5 units, this has increased by 5 units, this has increased by 5 units, this has increased by... So the difference between U's of any 2 points will still be the same because each has increased by 5 units. Clear? Someone will then say, well, I am going to choose UA as 1. So then all these UAI's will increase by 1 unit, but the difference in the U's between any 2 points will still remain the same. And that's the reason special values to U's don't matter. They are of no use. Right? All that matters is the difference in the U's, which will be the same irrespective of the choice of the reference point and the specific value of U assigned to the reference point. The difference in U's will remain preserved irrespective of the choice of the reference point and the specific value of U assigned to the reference point. It's going to remain the same. Are you in sync with me?
Yes, sir.
And that's why I said absolute potential energy at A does not matter. It's of no consequence. It's of no physical importance. But the difference in potential energies is important, and that will remain preserved irrespective of what my reference point is and what value of U I have assigned to the reference point. So the reference point could be out of convenience related to the physical situation, and the value of U assigned to that will also be out of convenience. Ideally, the reference point should be assigned a value U equal to 0. Are you all okay with this? Right? Now, yes, yes, yes. Any point could be the reference point, right? London, Patna, etc. Can I wipe this off? Which means now in this region, what I have in this region is every single point is tagged to a certain number by choice of a reference point and by assigning a number to that reference point, which would be looked upon dearly as the potential energy of the test particle at that point. I would end up getting scalars associated with every point of that region. These scalars will notionally represent the potential energy of the particle at those specific points. Right? So every point of this region is now characterized by a number, by a scalar. With every point, all that I said was every point now has been assigned a number. That's all that I said. Right? So every point is characterized by a scalar, a number. How did that happen? I chose a reference point. I assigned the value of U to that reference point, called it 0, for example, in this case. Could have called it anything else. Based on that, a value of U could be assigned to every single point of this region. And Therefore, what I have in this region is what's referred to as a scalar field. The earlier one was a vector field. The vector field told me what the force acting on the test particle is like at any given point. That's what the force vector told me. That's what the vector field told me. That's what the vector field told me. Now I have a scalar field. But then this scalar field has been arrived at with the help of calculating the work done between any 2 points, fundamentally. The work done between any 2 points has been computed, the difference in u's obtained, and then I assign numbers to every point of this region. A good scalar field has thus been obtained. And in this scalar field, all these numbers attached to different points are about the potential energy of the test particle at those points. Yes or no? Now, so by some means I obtain in that region the value of u for all sets of x, y and z's. Any point would be characterized by its coordinates x, y, z. So u at any x, y, z is known to me. U as a function of x, y, z. If someone gives to me x, y, z, I'll be able to calculate the u at that point, the number u at that point. This is the scalar field. This is the scalar field. Are you all in tune with me? Right? From the vector field, calculated from the vector field. But now I have conveniently moved to a scalar field, and that's exactly what I am going to demonstrate. Why it helps moving to this scalar field, how it helps moving to this set of numbers from those set of vectors, right? So there is a point A, and I assign it a value 0. There is a point A1, say I assign it a value -10. There is a point A2, I assign it a value -5. There is a point A3, I assign it a number -3. A4, 15, A5, 18, and so on and so forth. These numbers are assigned. This is available to me. There is a function of u in terms of x, y, z, which will help me calculate u. That means these numbers at any x, y, z. Given the coordinates of that point x, y, z, let's say I am able to calculate the u at that x, y, z. Right? I hope I am not confusing you. Huh? What numbers are the coordinates? These are the values of u at those points. These are the values of u at these points. This is u equal to 0. I mean, how can this be x, y, z, all of them? Tell me. Huh? No, but these are u's at these points. Each of these points will have a certain x, y, z triplet that will specify where this point is. Clear? Now, given this set of numbers, a one-time effort, and I get this set of numbers for every point in this region, right? Now, if I want to calculate, let's say, the work done in taking a particle from A4 to A1, I want to calculate the work done in taking the particle from A4 to A1. One thing that I could do is do a f dot dr, f dot dr, f dot dr, f dot dr, sum it up, calculate the total amount of work done. That's a lot of work, right? That's a lot of work and gets clumsy too. Don't want to do that. Once I have this scalar field at my disposal, at my service, I would want to deploy all these numbers. The work done from A4 to A1 would be negative of the change in potential energy, would be negative of the change in potential energy from A1 to A4, right? So this would be minus of u at the final point minus u at the initial point A4. And u at the final point, A1 is minus 10 minus u at the initial point is 15. 25 joules of work is done. And did it require any integration? No. And I could do this calculation for any 2 points of this region without taking recourse to complicated integrals, right? So dealing with this region with this set of numbers is lot more effective than dealing with a vector field given to me, f as a function of the position vector r, could just turn out to be horrendous, right? But if I have been able to find a u for every point of this region, then calculating the work done in this region between any 2 points is as simple as this. As simple as this. Do you realize that? So it makes sense to migrate from the vector description of the region to a scalar description of that region. Right? From the vector description of the region to the scalar description of the region. It makes sense. Are you fine with this or not fine with this? Got me? Now, say, so this is called the potential energy function. This is called the potential energy function. A function of x, y and z. A function of x, y, z. Given any x, y, z, I should be able to calculate the potential energy at that x, y, z. Let's say, by some means, I have been able to obtain the scalar field, the scalar description of the region, u at x, y, z, say, is given by x square y plus, say, x, y, z. I obtain this function somehow, right? Then at any x, y, z, I'll be able to calculate the potential energy. Say, for example, I want to calculate the potential energy at 0, 0, 0, it's going to be 0. At 1, 1, 1, it's going to be 2. And so on and so forth, right? So for given the value of x, y, z, I'll be able to obtain the potential energy at that point, right? So that's this is the scalar description of that region. This helps me obtain the potential energy of the test particle at any x, y, z. Clear? Now, my contention is, given u a function of x, y, z, given u a function of x, y, z, how do I obtain the force vector at any x, y, z? See, I would also want to have knowledge, given u a function of x, y, z, how do I obtain the force acting on the particle at any x, y, z? I would want to know that, right? Yeah, let's look at that. So essentially, I want to know, given u a function of x, y, z, it need not be this, it could be anything. This was just to make you feel comfortable that this is how we do the calculations. So u a function of x, y, z available to me. I want to calculate the force acting on the particle at any x, y, z, right? The force acting on the particle at any x, y, z I want to know. The force at any x, y, z will have 3 components. A component in the x direction, a component in the y direction, and a component in the z direction, right? So this will have a component in the x direction. That means this is the magnitude of the force in the x direction. And its value will depend on where the point P is. The point P is x, y, z. That means Fx in a very general sense will depend on all 3 x, y, z, the position of that point. So x component of the force will depend on x, y, and z. I cap, there is a x component of the force whose value will depend on where the point is. So it will be a function of the coordinates of that point, and it will be directed along the x direction, right? I cap. There is a y component of the force at any x, y, z. The y component of the force will also depend on where the point is. therefore will depend on the coordinates x, y, z. So this will also be a function of x, y, z in general, and it will be along the y direction. So j cap. Is that all right or not all right? Right? There is a z component of the force, k cap.
Why will it be dependent on all three and not only?
No, why? Why should it not be? It will depend on where the point P is. The x component of the force will depend on where the point P is. That means what its coordinates are, x, y, z. It's, when I say fx, all that it doesn't mean that it depends on the x coordinate. All that it means it's the magnitude of the force, component of the force, parallel to the x axis. Doesn't mean that it will depend only on the x coordinate of the particle. It will depend on where the particle is. That means the coordinates of the point x, y, z. Isn't it? The component of the force in the y direction will depend on where the particle is, x, y, z. The z component will depend on where the particle is. It's just that this fx, fy, fz will be directed along the x, y and the z directions. Are you okay with this or not okay? I want to know this. Given u a function of x, y, z, I want to know the force vector at any x, y, z. I want to know the force vector at any x, y, z. It will have three components, and each of the components will depend on where the particle is. That means the coordinates of the particle, x, y, z. Right? Now, even before I do that, let me in a laymanish fashion, leaving you a little incomplete with this discussion, but promising to get back with more authenticity when you are mature enough to take that. But for the time being, a makeshift arrangement between you and me about a proper understanding of this, but then, just kind of making my assertions believable. That's about it, but not putting them on solid footings at this point of time. Just a few things. I will bypass a few things, tell you a few things, arrive at a result which we'll use right now, but you may not necessarily understand how exactly, right? But then once I have taught more calculus to you, I'll be able to come back to it with proper authentic explanations, right? Now, so the next few minutes might be a little bit of an ordeal, but deal with it. Okay? Now, first of all, let me tell you what a partial derivative is. Let me tell you what a partial derivative is. Just because I have put a disclaimer before I started this discussion doesn't mean you will get into a resigned state, forcing yourself to not understand this. Alright? There would be some elements that will remain oblivious at this point, but there would still be an overall feel for things. Okay? So, first of all, what's a partial derivative? Say, if I have a function f, which is, say, x squared y cubed plus z squared x, suppose. This is a function of x, y, z, right? Now, when I say differentiate f partially with respect to x, differentiate f partially with respect to x. What, first of all, the notation for that is dou f dou x, dou x of f. It's dou x of f. Instead of d dx, it's dou, right? So don't become a dodo. Understand this dodo, however. So this is like differentiate f with respect to x partially is written as dou x of f. Dou x of f. It means differentiate f with respect to x as if y and z are constants. It means differentiate with respect to x as if y and z are constants. That's what is meant by dou f dou x or dou x of f. Dou x of f. Differentiate f with respect to x partially means assume that y and z are constants. Right? That's the partial derivative of f with respect to x. Now, so if I have to differentiate this with respect to x as if y and z are constant, what would that be in this case? 2x y cube plus z squared. Differentiating with respect to x as if y and z are constants. Yes or no? Purohit, bhai, where is the confusion? Huh? I'm saying differentiate f with respect to x as if y and z are constants. This is f. Assume that y and z are constants. So what's the derivative of this? 2x y cube. What's the derivative of this? Z squared. Right? That's the partial derivative of f with respect to x. Yes or no? Yes, sir. Right. If I said dou f dou y means differentiate f with respect to y partially, that means as if x and z are constants. As if x and z are constants. So if you do this x and z constants, then this would be 3y squared x squared. This is no y here, that's going to be 0. That's dou f dou y. If I said dou f dou z, differentiate partially with respect to z, f. So it's as if you'll assume x and y are constants. Then this will be 2zx. This will be 2zx. That's the partial derivative of f with respect to x, y and z. Now,
What would be the ddx of f?
ddx, there is no ddx of f. ddx of f means the total derivative. Okay, now that I'll come to that also. That will be dou f dou x into dx, dou f dou y into dy, dou f dou z into dz. That's df, but don't bother about df. Right? df, the change in f, essentially he's just pushed me into those domains, but I don't think you need to know that right now. If I want to find the change in f, then that's going to be rate of change of f with respect to x alone into dx plus rate of change of f with respect to y alone into change in y plus rate of change of f with respect to z into dz. That's df. That's only for your mental solace, not that you will understand anything of this. Okay? Okay. So can I assume that you have understood how to differentiate a function partially? Right? And what this notation dodo means? Right? Good. Now, Khoka, same thing though. Say, I want to differentiate sine xz with respect to x, keeping y and z constant, keeping z constant in this case. So first, apply chain rule. Differentiate with respect to xz, cos xz, and xz with respect to x, z. As if z is constant, if you want to differentiate, chain rule. Differentiate with respect to xz, that's cos xz, and then xz with respect to x, as if z is constant, that's going to be z. So z cos xz, same rules of differentiation apply, except that you're going to deal with y. If you are differentiating partially with respect to x, you want to keep y and z constant. The same way you want to differentiate, those rules are not changing. Trigonometric, exponential, logarithmic, everything remains the same. Chain rule applies. Got me? Yes or no? Yes, sir. Yeah. Okay, now, having understood this, assuming let me Let me then take you to where I'm intending to take you. Say what's known to be is, say f the force vector, suppose a function of x, y, z. It will have an x component which will be a function of the position of the particle x, y, z. It will have a y component f, y. It will have a z component f, z, k cap. Right? Now, at a certain point P, let's say, at a certain point P, which is coordinates x, y, z, coordinates x, y, z, the force acting on the particle will be this F. F at this point, right? F at this point. F at x, y, z, that will be the force vector acting at this x, y, z at the point P. On the particle when it's at the point P. That's what I mean. Clear? Now, what I do is, I mentally imagine the particle to be displaced, parallel to the x-axis. If the particle is displaced parallel to the x-axis, y and z don't change. Yes or no? Say this is the x direction, this is the y direction, and this is the z direction pushing into you, right? So if I move the particle parallel to the x-axis, is the y and z coordinates remaining the same or not? Yes. Right? Only x is changing. If the particle is moved parallel to the x-axis, only the x coordinate is changing. Y and z remain constant. Okay, so now let's say the particle is moved to P prime, where its y and z remain the same. It's moved parallel to the x-axis, it's displaced parallel to the x-axis, where its x changes by an amount dx, say, and its y and z remain the same. In the conservative force field, the particle goes from P to P prime, parallel to the x-axis. Right? Now, this is a very small amount of displacement dx. It looks large. Don't get misled by that. Small. Right? Dx. For this very small displacement, the component of the force in the x direction will not change. What's the component of the force in the x direction? Fx is the component of the force in the x direction. It remains what it was at P, practically what it was at P. For this infinitesimally small displacement in the x direction, the x component of the force remains Fx. Right? And this is the y direction, say this is the x direction, this is the y direction, and this is the z direction, right? There is a force component in the y direction, Fy, and there is a force component in the z direction, Fz. These are the components of the forces of the field. Yes or no?
Yes, sir.
Right? Now, I want to calculate the work done by this force. I want to calculate the because x is changing by an infinitesimally small amount dx. So there is hardly a change. Right? When x, that's the whole idea of that. F dot dr, for that small dr, F remains practically the same, right? So, got me? Now, tell me this, when the particle is transported from P to P prime, what's the work done by the y component of the force? 0. Why? Because Fy and dx are perpendicular to each other. Fy and dx are perpendicular to each other. So the work done by Fy is 0. Fz, work done is 0 because Fz and dx are perpendicular to each other. What's the work done by Fx? Fx into dx. Work done by Fx is going to be Fx into dx. So if I have to then commit to the total amount of work done by this force, then that's contributed only by Fx. So the total work done by the field, therefore, to have the particle migrate from P to P prime, the total amount of work done by the forces of the field would be Fx into dx. Fx into dx. Keeping y and z constant. Keeping y and z constant. I have maintained y and z constant, yes or no? Right? Keeping y, z preserved. How about it? But the work done by the forces of the field must also be negative of the change in potential energy by definition. It's a conservative field. It's a conservative field. Work done by the forces of the field must be negative of the change in potential energy, right? So this is minus du. Du is the change in potential energy. Du is the change in potential energy. This will therefore be negative of the change in potential energy, right? Right? All of this is as if y and z are constants, right? So we end up getting the x component of the force at xyz. This is the x component of the force at this point into dx is minus du, change in potential energy, on the pretext that y and z are constants. Yes or no? I'm trying to go as elementary as possible and communicate these ideas. I hope you understand most of it, right? Huh? No, there is, agreed, there is no, because it's also because Fy is perpendicular to dx, which means the x component of the force must be minus du dx, keeping y and z constant. Yes or no? Yes, sir. Thank you. Which means, but differentiating u with respect to x, keeping y z constant is dodo. Here's where the dodo comes, minus dou u dou x. Then you don't have to write y and z constant. The moment you put a dodo, taken care of, right? Right? So x component of the force is minus dodo x of u. Similarly, exactly the same way, you will get y component of the force as minus dou u dou y. Z component of the force is minus dou u dou z. Yes or no? Has it gone through you? Has most of it gone through you?
Yes,
Through most of you? Right?
Sir, but how can you assume that it moves parallel to?
No, I'm causing it, yaar. That's my choice. Arey Baba, I've just caused the particle to go from P to P prime. How can you challenge that? I was seeking fx, so I did this. Yes or yes? I will assume that. See, to calculate Fy, I want Fy to get. See, why did I cause the particle to move parallel to the x-axis? So that I could expose Fx. That was a convenient way to expose Fx. And obliterate Fy and Fz. So that I could have Fx on the front and make Fy and Fz go into oblivion. I would want to move parallel to the y-axis so that I could expose Fy, and Fy is available to me. Exactly the same way, right? I'm carrying out these operations so that Fx, Fy, Fz could be independently exposed and be made available for consumption, right? I like that pitch. Yes, be energetic, even if it means going to the extent of being a little rowdy, etc. in the class. It's good. I would prefer you being very energetic, even if it means a little playful and indulgent. That's all right. Good. So then, yeah, as long as you don't blow him away from this place, make sure the decibels are not that powerful. Therefore, hey, I have seen you after a long time in the class, Ishan. Where had you been? हाँ? अरे देख के तो चंगे लग रहे, अभी ठीक हो ना? ठीक है. Now, okay, so which means suppose someone gave me this scalar field u. That means I was given the value of u at all xyz's in a certain region of a conservative field. Okay, say the u at any xyz, some joker told me, is x cube yz plus x square y. At any xyz, this was, let's say, the potential energy of the test particle in a certain conservative field. So from this, I would want to be able to obtain the value of the force vector at any xyz. So I would want to know the x component of the force at any xyz. I would want to know the y component of the force and the z component of the force, right? And what we just obtained was the following: fx as minus dou u dou x, x component of the force. That means differentiate u with respect to x, keeping y and z constant, right? This is what it meant. So this is like minus 3x squared yz plus 2xy. Yes or no? This was the x component of the force at any xyz, right? The y component of the force at any xyz will be obtained by minus dou u dou y. That means minus differentiate with respect to y as if x and z are constants. So you get like a x cube z plus x squared. Yes or no? Differentiating with respect to y as if x and z are constants. So this will give me the y component of the force at any xyz. Clear? The z component of the force is minus dou u dou z differentiate with respect to z, keeping x and y constant. So that's gonna be x cubed y. So the force vector is going to be given by the description of the force at any xyz is going to be given by x component of the force I cap, y component of the force j cap, z component of the force k cap, fx, fy, fz known. So now I have the vector description of the region. So from the scalar description we could migrate to the vector description of that region. Got me?
Yes, sir.
Did you assimilate most of it?
Yes, sir.
All right. So we got our first level of understanding of a conservative field and a basic understanding of what really potential energy is all about, right, in terms of the field, and how we could migrate from the scalar description u of the region to a vector description f with the help of fx's minus dou u dou x, etc. Now let me come to terms with a very important aspect of all that we are studying in work, which is called the classical work energy theorem. The classical work energy theorem. CWE. Sometimes we'll just call it WE or CWE, classical work energy theorem. So, you know, there could be a particle or a system of particles, and they could be acted upon by forces F1, F2, F3, and so on and so forth, say Fn. Based on the displacement of the point of application of each of these forces, we could calculate the work done by each force, right? Let's say the work done by F1 was W1, the work done by F2 was W2, the work done by F3 was W3, the work done by Fn, let's say, was Wn. This is the work done by all the forces acting on the particle or the system of particles, right? This, from classical work energy theorem, is supposed to be change in kinetic energy of the system, delta Ke, final kinetic energy minus initial kinetic energy. This is change in kinetic energy of the system. Now, even before I venture into giving you a formal proof of this, let's learn how to apply this, right? Work done by various forces will be change in kinetic energy, final kinetic energy minus initial kinetic energy. Now, one thing that remains pending is a little bit about springs. We got started with the spring element, and we learned a little bit about the force constant of the spring. We learned the force acting on a particle when connected to one end of the spring forces, right, kx kind of a thing, and the direction of the spring force always being such so as to restore the spring to its natural state or free state. Okay, now the spring force is a very typical example of a conservative field. Say this is a spring with force constant K, and say this is the natural state of the spring. This is the natural state of the spring. Let's say L naught is its natural length. L naught is its natural length. Clear? Let me measure this point as x equal to 0. this is x equal to 0, and let's say this is the positive direction of the x-axis. This is the positive direction of the x-axis, right? Now, when I pull the spring, apply an external force and start pulling the spring. Initially, elongation in the spring is 0, so spring force will be 0. But as I keep pulling the spring gets stretched more and more, and the spring force grows. The spring force grows. So it's a non-constant spring force. It's a non-constant spring force, right? If it's a non-constant spring force, let's say at some instant this is the end of the spring P. After a while, the end P will come to this position, call it P prime. And the spring would have got elongated by an amount x. The spring would have got elongated by an amount x. Right? So the free end of the spring has come to this point. The external agent is applying a force this way. What would be the direction of the spring force? Leftwards. Leftwards, this way, right? So the spring force would be at this juncture, the spring force would be of magnitude kx. The spring force would be of magnitude kx. I've shown the direction, the magnitude kx, but leftwards as shown, right? Now, if I enable a small displacement, a further displacement dx to the right, if the spring gets further displaced to the right by an amount dx, what's the work done by the spring force? The spring force is leftwards, but the displacement of the point of application is rightwards. What's the angle between force and displacement? 180 degrees. So what would be the work done by the spring force? Minus kx into dx would be the work done by the spring force, yes or no? The spring force is leftwards kx, the displacement is dx rightwards. What's the angle between force and displacement? 180 degrees. What's the work done by this force? Magnitude of the force into magnitude of the displacement into cos 180 degrees, right? That's the work done. X is the elongation till this point of the spring. For a further elongation of dx, the small amount of work done for a further elongation of dx would be the force at this point into displacement corresponding to this point into cos 180 degrees, yes or no? That's the work done to enable a further displacement dx, right? So the work done for this, as you can see, is going to be work done by the spring force, so to say. Work done by the spring force. This is the work done by the spring force, and therefore the force at different points, see, the spring force is varying. While this end goes further and further to the right, the spring force is varying. It's not a constant force, it's varying. Therefore there is a force field associated in the x direction. There is a force field associated in the x direction. With every value of x, I can associate a spring force vector, yes or no, right? So, and this force field created by a spring is a conservative field, Now, the work done by the spring force is going to be minus kx into dx, as you can see. Right? Now, if I had the task of displacing the spring by a total amount x1, if I want to elongate the spring by a total amount x1, from P I want to go to PF with a total displacement x1, total elongation x1 of the spring. Then to calculate the total work done, what I do is, at different values of x, I take a force, spring force, into displacement. For all values of x, starting from x equal to 0, this is x equal to 0 to x equal to x1. I take different x's, displacement corresponding to those x's, and calculate the work done. And I sum up all such numbers. I sum up all such numbers starting from x equal to 0 to x equal to x1. When I sum up all those numbers, then that will be the total amount of work done by the spring force. That's going to be the total amount of work done by the spring force would be sum of all of this, where x runs from 0 to x1. That's the total amount of work done by the spring force. So which is like minus half k x1 squared. That's the total amount of work done by the spring force, yes or no? Right? Now, direction of the work done. Work done is a scalar. What do you mean by direction of the work done? It will be positive or negative, or it could be 0. The f dot s is a scalar. It doesn't make sense to talk of direction of the work done. It's just the work done, which could be positive or negative, right? Is that all right or not all right? Which means, if the spring is elongated by an amount x1 over and above its natural length, then the work done by the spring force would be minus half k x1 square, starting from x equal to 0 to x equal to x1. If it's compressed by an amount x1, that means you replace x1 by minus x1, then it will still be the same. Work done by the spring force will still be the same. It will still be minus half k x1 squared on replacing x1 by minus x1, right? Therefore, whatever I am saying of elongation of the spring by an amount x1 will also be true for compression of the spring by the same amount. Yes, right? Now, from this point, what it really means, if this is a spring, this is the natural state of the spring. If it's elongated by an amount x, if P goes to Pf, elongated by an amount x, then from x equal to 0 to x equal to x, the work done by the spring force is going to be minus half k x squared. Instead of x1, you have x. That's all, right? That's a work done by the spring force from x equal to 0 to x equal to x, right? But the work done by the spring force, it's a conservative force, so the work done by the spring force is negative of the change in potential energy. Is negative of the change in potential energy by definition. So this from definition is minus of potential energy at Pf minus potential energy at P. What is P? P is the natural state, that is x equal to 0. Right? Now, in this case, I have no way to find UPF and UP, but I have a choice that I can conveniently make. I can choose the point P, the natural state of the spring, as my reference state. If I choose that as a reference state, then I might as well call UP to be 0. I could choose to call the potential energy at P to be 0. If you don't want to do that, don't do that. That's your choice. But I'll do that. UP is 0. Right? Nothing cardinal about it. This is not God sent. It's just out of convenience. Right? So if I did that, then that will give me the potential energy of the spring at Pf as half k x squared. So if the spring is elongated or compressed by an amount x, bless you, it has potential energy which is half kx squared. This is also called the elastic potential energy of the spring. This is also called the elastic potential energy of the spring. or the sometimes also called the deformation energy, also called the strain energy. All of this mean the same, right? Now, can I wipe this off? Suppose we had a spring that was already deformed. Okay. This is x equal to 0, the natural state of the spring, and say I have a spring which is already elongated by an amount x1. I have a spring which is already elongated by an amount x1. Now, from this point, so there is a spring force at this point which is kx1 acting leftwards at this point. Now, I elongate the spring further. I elongate the spring further, and the free end goes from P to Q. At Q, the elongation in the spring is x2. See, the elongation or compression is measured from the natural state. This is the natural state of the spring. This is the natural state of the spring. All elongations or compressions are measured with respect to the natural state, the free state. All right. So the end goes from P, where it's in a state of extension x1, to the point Q, where it's in a state of extension x2. Now, between P and Q, the elongation of the spring was variable. So the spring force, which was kx, was also variable. And I want to be able to calculate the work done by the spring force when the end goes from P to Q. When the end goes from P to Q, I want to be able to calculate the work done by the spring force. You know what I'm saying? Now, at P, what is the potential energy of the spring? Half k x1 square is the potential energy of the spring. At Q, what's the potential energy in the spring? Half k x2 squared is the potential energy in the spring. The work done by a conservative force will always be negative of the change of potential energy, right? So the work done by the spring force will always be, because it's a conservative force, will always be negative of the change of potential energy in the spring, right? Which is minus of final potential energy minus initial potential energy. That's the work done by the spring force. Negative of the change of potential energy. Negative of final potential energy minus initial potential energy. Right? Now, can I wipe this off? Was? X. No. I'm saying someone gave to me a spring already elongated. ये x1 सोचो दहेज में आया तुम्हारे, तुम उसको x2 तक ले गए, ठीक है? All right, so we are given a spring in an elongated state, and I further elongate it by an amount x2 minus x1. That means the elongation is x2. I bring it to an elongation state x2 from an elongation state x1. The work done by the spring force would be negative of the change of potential energy. The potential energy of the spring here was half k x1 squared. The potential energy here was half k x2 squared. Negative of uq minus up will give me the work done by the spring force. when I cause the spring to go from P to Q. Does it settle in your head? Because we're going to use this result very often. So must take proper notice of this. Clear? Now, yes, please. Has nothing to do with work done by the spring force, if you allow me to say that. Work done by the forces of the field, like I mentioned at the very onset, has nothing to do with what other Johnnies are doing, right? Even though the external force could be 1 million newtons, the spring force will still be kx depending on x. It will not get very greedy, right? So work done by the spring force depends on what the spring force is, and the displacement from instant to instant will determine the work done by the spring force, not what the external agent is doing, right? So just a quick mention, since all of you know this, but let me once again. This was, let's say, the ground, a reference, all right? A particle was taken from the point P to the point Q at a height h above the ground. At a height h above the ground, right? So during this journey, what was the gravitational force? mg downwards, right? So this is the gravitational force. What's the work done by gravity? mg is downwards, h is upwards. Angle between mg and h is 180 degrees. So work done by gravity is minus mgh. But gravity is a conservative force. So work done by the forces of the field would be negative of the change of potential energy. So this would be minus of uq minus up. Minus of final potential energy, that is at Q, minus initial potential energy, that is at P. Now this P could be my reference point. I might as well choose UP to be 0. Might as well choose UP to be 0. Or if you don't want, don't. But I'll do. UQ then will be MGH. So this MGH, which seems falsely to be the potential energy at Q, is actually the difference in potential energies between Q and P, right? So if someone said work done or potential energy is energy by means of position or configuration, how will you obtain this MGH? Tell me. It could also have been mgh squared, h is the position, mgh cube, mg sin h to the power h cubed, right? Therefore, come to one basic conclusion: that definition is inept, is deficient. Okay, energy by means of configuration or position, that's a property of this, all right, but that's not the definition. That's not the definition of potential energy. And okay, so the work done from P to Q along this path is minus mgh. Work done by gravity is minus mgh. But if I had to take the particle from P to Q along this path, then what's the work done by gravity? It will still be the same. Along this path, same. And if I go this way, this way, this way, this way, and come back to P, what's the work done by gravity? Going to be 0. Work done in a closed path by gravity will be 0. P to P, no matter where I went and how I came, will still be 0. Right? Got me? Okay. Now, there are checks that we perform, in the sense we do calculations for an arbitrary path. See, if you if you have gone through my previous discussion, I calculated work done by some fields, right? For example, one of the fields was uh, a yi cap plus xj cap. Do you realize that I took an arbitrary path and the work done did not depend on the path because I didn't have knowledge of the path. I took a dxi cap, a dyj cap, and then the work done was y dx plus x dy, which is dxy. And nowhere did the path interfere. So if the path did not interfere in computation of f dot dr, then that field would be classified as a conservative field. Got me now? Same thing with mg now. In all these cases, let's say if I went from P to Q this way, at an intermediate point, this was mg, right? A further displacement was like this. So then, what's the work done by mg for a displacement dr along this path? Would be, now all that is important is component of dr in this direction. The component of this dr in this direction is perpendicular to mg will not participate in work done, but this component will participate in work done. So if this change was say dx, then what's the work done by mg? See, this is say dl, then the work done by mg is going to be minus mg into dx. The total work done would be sum of all of this, right? Where dx's are vertical. Say this was at x, this dx was at x. So x runs from say 0 to all the way to x equal to h, right? So the total work done would be x equal to 0 to x equal to h, which is minus mgh, path independent. So this must have been a conservative field. Did I have knowledge of this path? This was arbitrary. I never used anything about the path actuals in calculating the work done by the field. The field therefore must have been a conservative field. That's the whole idea, right? So do a f dot dr for any arbitrary path, and if that integration is not path hungry, if it does not inquire you about the path, then the field ought to be a conservative field. That is how we evaluate the field and assess the field for its character. Sounds good? Now, coming back to, so this was a little detour, but in this session we started with the work energy theorem, where I told you that if a particle or a system of particles was being acted upon by a set of forces, then, and the point of application of each of these forces got displaced, therefore there was work done by each of these forces, and I told you then that the algebraic sum of the work done by all these forces, because algebraic, because some of these might be positive, negative, or zero, work done could be positive, negative, or zero. Therefore the algebraic sum of the work done by various forces acting on a particle, summation wk, work done by various forces, w1 plus w2 plus w3 plus wn, this must be the change in kinetic energy. This was classical work energy theorem, WE. This was classical work energy theorem, WE, right? Now, let me illustrate it with some very basic, simple things. Okay. See, suppose this was a mass m on a rough horizontal surface. With mu k as 0.1, with mu k as 0.1, right? This was imparted a velocity v naught equal to 2 meters per second at time t equal to 0. After a while, so this will retard. Why would it retard? Because frictional force will act backwards. Realize that there is mg, say m was 10 kgs. So there was mg which is 100 newtons. 100 newtons acting downwards. There is normal reaction R which is 100 newtons acting upwards. Right? Frictional force would be kinetic friction, mu k into n. N is mg in this case, R 100 newtons. So frictional force is mu k into R. Mu k into R means 0.1 into 100 means 10 newtons acting backwards, right? Now let's say it acquired a velocity say v1 equal to 1 meter per second. After a while, it's going to retard under the influence of this frictional force, kinetic friction, and during this journey, say it traveled a distance s meters. It travels a distance s meters, right? I want to apply work energy theorem to this situation. Now, essentially we have work done by R, work done by gravity, plus work done by friction. That must be change of kinetic energy, consequence of classical work energy theorem. These are the three forces acting. Now, what's the work done by R? Because R is this way, displacement is perpendicular to R, so work done by R must be 0. What's the work done by gravity? 0, because force perpendicular to displacement. What's the work done by friction? Minus 10 into s, because the angle between this force vector and this displacement vector is 180 degrees. So minus 10 into s, and that must be change of kinetic energy. That means this must be half of mass, which is 10 into v1 squared minus v0 squared. Change of kinetic energy, right? Half mass v1 squared minus v0. So this will enable computation of s. This will enable computation of s. Clear? Let me change this situation a little more. Okay. Suppose there was a spring, a force constant K, and the spring was in its natural state. And the spring was imparted a velocity v naught to the right. The spring was imparted a velocity v naught to the right. Clear? Now, when and left alone, right? And let's say this surface was smooth. Let's say this surface was smooth. Initially, the spring is in its natural state, so spring force is 0. But while this mass moves to the right, it will elongate the spring. Therefore, the spring force will start to act leftwards in this direction. It will therefore start to retard the particle. It will start to retard the particle. So this was, let's say, x equal to 0. So the velocity will decrease, particle of mass m. So after a while, the free end of the spring comes to p prime, and the mass acquires a velocity v1. The mass acquires a velocity v1. Let's say the elongation in the spring till this point is x1. I want to apply work energy theorem between these two states. I want to be able to apply work energy theorem between these two states. So then, force is acting. There is spring force acting, which is varying. Why? Because x, the elongation, is varying, right? There is mg, which is not varying. There is normal reaction n, which is mg, which is not varying, right? So between this state and this state, I can apply classical work energy theorem. Okay. Work done by mg, 0, because mg is perpendicular to the displacement x1. Work done by normal reaction, 0. Work done by the spring force will be negative of the change of potential energy, negative of the change of elastic potential energy. Now this was x equal to 0, so potential energy was 0 here. At this state, what is the potential energy? Half k x1 squared. Work done by the spring force will always be negative of final potential energy minus initial potential energy. So the work done by the spring force would be minus half k x1 squared. Right? Are there any other forces acting? No. And this then must be change of kinetic energy. That means this must be half m v1 squared minus v0 squared. No, I just gave it an impulse, velocity v0, and left it. I let it go. If you like, let me now keep an external force also acting on it. Let's do that. Okay, let's add more frills to that. What I'll do is, same situation, I'll add an external force. I'll make this surface rough. Let's do that. Okay. So this was the mass m, and say mu was the coefficient of friction, and an external force F acted. Right, and let's say this mass started from rest. This started from rest. A constant external force is acted, and this mass started from rest. And this was x equal to 0, the natural state of the spring. Right? After a while, the spring elongates. The spring elongates by an amount x1. The spring elongates by an amount x1. And let's say the mass develops a velocity v. The mass develops a velocity v. Let me apply work energy theorem to these two states. Clear? What are the forces acting on it? There is F, of course. There is mg downwards. There is normal reaction, n upwards. And there is frictional force, kinetic friction, which would be mu mg to the left which means when we apply work energy theorem, what's the work done by n? Why? Because n is perpendicular to displacement x1. What's the work done by gravity? 0. Yeah, I can answer your question. Yes, yes, there is spring force also. There is spring force also. Initially it's 0. There is spring force also, which is initially 0, but builds, right? So work done by n 0, work done by mg 0. What's the work done by F? F into x1 is the work done by F, right? What's the work done by N? 0. What's the work done by mg? 0. What's the work done by the spring force? Negative of the change of elastic potential energy, right? So the elastic potential energy is 0 here. The elastic potential energy is half k x1 squared here. So minus half k x1 squared, that's the work done by the spring force. And there is work done by the frictional force, which is minus mu mg into x1. Frictional force is leftwards and displacement x1 is rightwards. So minus mu mg into x1, and this must be change of kinetic energy. That means this must be half m v squared. Right? Let's look at some more. No? Can I wipe this off? Suppose spring force with force constant K. Ideal spring. This was the natural state of the spring. X was 0, elongation was 0 in this state. There was a mass m connected to the spring, right? And there was a force F acting to the right. There was a force F acting to the right. And let's say this surface was smooth, frictionless. Say this surface was smooth, frictionless. Now, let's analyze the physics of this situation. Let's understand what all is happening here. Let's understand what all is happening while this constant force acts on the spring. To what extent the spring could go. Okay. Now, the forces, there is mg and there is n. I'm not designating those forces. Those are passive forces in terms of work done in this situation, not always. Therefore, no point cluttering this. Okay. The spring force is initially 0. What's the initial acceleration of the mass m? F by m. F by m is the acceleration of the mass m initially to the right. Right? The mass is solely under the influence of the force F horizontally at the initial instant. Right? And I'm assuming also that the mass, say, starts from rest. The mass starts from rest. Now, this moves to the right. This moves to the right. While this moves to the right, after a while, the spring would have got elongated by an amount x, right? The force will still be F, and the spring would have got elongated by an amount x. Now, if the spring gets elongated by an amount x, what would be the spring force? kx leftwards would be the spring force. What would be the acceleration at x? Hey, what acceleration at x? F minus kx by m. Right? Now, see what is happening. As the spring is getting more and more elongated, this kx is growing in stature. So acceleration is decreasing because f is remaining the same, right? F on a relative scale is getting weaker compared to kx, right? But as long as f is greater than kx, the acceleration would be to the right. Even though the acceleration might be decreasing in magnitude, but the velocity continues to increase. See, at one instant the acceleration is 5 meters per second squared. Next instant the acceleration is 4 meters per second squared, 3 meters per second squared. Agreed that the acceleration is decreasing, but the velocity will still increase. As long as it's a non-zero acceleration, the velocity will increase. If it's a decreasing acceleration, all that it means is velocity is increasing at a smaller and smaller rate. That means if the acceleration is decreasing, and if in the first 1 second the velocity has increased by 10 meters per second, then in the next second it will still increase, but not by 10 meters per second, it will increase maybe by 8 meters per second, but it will still increase. That's the meaning of a decreasing acceleration. The velocity increases, but at a decreasing rate. Am I confusing you? No. So the body continues to move to the right with increasing velocity. At some point, say x equal to x naught. At some point, say x equal to x naught. Some x equal to x naught. The spring force manages to be exactly equal to the externally applied force, right? At some x equal to x naught, the spring force becomes equal to the externally applied force. The net force will be 0 then at this point. At this point, F net will be 0. Right? At this point, the F net will be 0. Acceleration will be 0 at this point, right? Acceleration at x equal to x naught will be 0. And what is this x naught when the acceleration becomes 0? At x naught equal to f by k. At x naught equal to f by k, the acceleration becomes 0. Does it make sense? That means the body comes to a state of equilibrium at x equal to x naught. The body arrives at a state of equilibrium. So this is an equilibrium position, EP, call it EP, equilibrium position, where the spring force exactly balances the externally applied force. Right now? Does it mean that the body will come to rest? No, because by this time the body would have developed a certain velocity v equal to v naught. The body would have developed a certain velocity v equal to v naught by the time it arrives at the state. So even though the net force at this instant is 0, the body has a rightward velocity v naught. And what would this velocity v naught do? It will further stretch the spring. It will further stretch the spring. So the spring gets stretched further. Now at this point, the spring force is exactly equal to F. But beyond this point, do you realize that the spring force will become larger than F? And if the spring force becomes larger than F, just slightly beyond this point, then this will begin to retard. The velocity will decrease beyond this point. From this point to this point, the velocity increased. From this point onwards, from the equilibrium position onwards, the velocity will decrease. the velocity will decrease. The body begins to retard, which means after a while you would expect, because the spring force becomes larger and larger, so the retardation grows in magnitude. If the retardation grows in magnitude, the velocity decreases at a faster and faster rate, right, from this point. Therefore you would expect at some x equal to xf, at some x equal to xf, the velocity to have become 0. The velocity would have become 0 at some x equal to xf, because it's retarding beyond this point, right? Now understand this. I know the equilibrium position. Ax naught, equilibrium position is x naught equal to f by k. When the spring elongates by an amount f by k, it's in equilibrium. The mass comes to equilibrium, but it does not come to rest. It's capable of moving further, right? But therefore I would like to know the velocity of the particle in equilibrium position. I would want to know the velocity of the particle when in equilibrium. What I could do is, I could apply work energy theorem between this state and this state. Between this state and this state, I choose to apply work energy principles, right? Okay. Work done by n and mg 0. What's the work done by F? So from an initial state, initial to equilibrium, from an initial state to an equilibrium state, what's the work done by F? F into x naught, F into x naught, right? What's the work done by the spring force? Minus half k x naught squared, negative of the change of elastic potential energy, right? So work done by the spring force would be minus half k x naught squared. Work done by mg and n is 0, right? And from work energy theorem, this must be change of kinetic energy. Final kinetic energy, half m v naught squared minus 0, right? So this is half m v naught squared. Now this gives me ready access to v naught, because x naught is known to us. X naught was the equilibrium state and x naught was f by k. So I can plug into this x naught equal to f by k and obtain the velocity of the particle in the equilibrium position. This position sometimes is also called the mean position. Equilibrium position, or sometimes also referred to as the mean position.
After f becomes equal to kx naught, after this equilibrium instant, the body will not move in this direction because kx increases.
If the agreed, but the particle has a velocity to the right. As long as it has velocity to the right, it will continue to move to the right. Any particle will move not based on its acceleration but based on its velocity, isn't it? I mean, when I chuck a particle up, mg is acting downwards, but the particle is still moving upwards. It will continue to move upwards till such time that its velocity reduced to cipher, right? So it will continue to move to the right and till such time that its velocity becomes 0. Then spring force will take over and will start bringing the particle to the left. So I know the velocity of the particle in equilibrium, therefore, right? Now what is xf? Do you realize that beyond this point the particle will not go any further? Therefore xf must be the maximum elongation produced in the spring. Xf must be the maximum elongation produced in the spring. This must be the state of maximum elongation. I want to know that. I certainly want to know that. So between this state and this state, can I apply work energy theorem? Yes, I could, right? So initial to final, initial to maximum elongation. So I apply classical work energy theorem from the initial state to a state of maximum elongation. Right? Okay. From this point to this point, what's the work done by F? F into XF. What's the work done by the spring force? Negative of the change of elastic potential energy. That means minus half K XF squared. And this must be equal to change of kinetic energy. Change of kinetic energy, right? Change of kinetic energy means final kinetic energy is 0. Initial kinetic energy is also 0. 0 minus 0 is approximately 0. Right? Yes or no? So this gives me XF equal to 2F by K. 2F by K. Isn't it? Which is twice X naught. Do you see that? Twice X naught. Because F by K is X naught. So this is twice X naught. So the particle has gone X naught units for equilibrium, X naught units further, then comes to this state, and 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 this state. Down the line we'll learn in oscillations that it's going to oscillate about this equilibrium position, mean position, with an amplitude X naught to the right and an amplitude X naught to the left. Don't bother about that though. Let this be understood in light of work energy theorem, right?
So what will happen after the last position? It will come back to
Yes, yes, because F is this is F and this is KXF. Velocity is 0 and KXF is larger than F, so it will move leftwards.
so it will again reach the equilibrium.
It will again reach the equilibrium position. It will go again. No, wait. Yes. It will come to this point. अबे ससुरे zero yoga. Because once it comes to the equilibrium position, right, this F becomes larger than Kx. Prabhu? Right? Got me? You understand this, right? Huh? Not a problem. Thank you. All in place? Even before you start tossing the coin, let me. Huh? Where? The previous case I told you how to calculate the work done by friction. Then, see, reason I didn't include friction in the second case, I could have done that, but what would happen is it will continuously decrease in amplitude and will eventually come to rest. In this case, it will never come to rest. No, in the sense, it will never stop oscillating. In that case, it will eventually stop oscillating. Shanti se mein, right? One quick remark about friction. See, if this was a mass m, on a very long platform, say capital M, and this rests on a smooth surface, this was, let's say, time t equal to 0. This was given a velocity v1 and this had a velocity v2. And say v1 was larger than v2. Say v1 was larger than v2. Clear? Now if v1 was larger than v2, friction on small m will act leftwards and friction on capital M will act rightwards, right? So there is, and what's the nature of friction? Fk. What's the nature of friction acting on this? Fk, to the right. All of you understand this, right? Of course, the velocity of the mass on top will go on decreasing. The velocity of the lower mass will go on increasing. Yes, after a while, they will acquire the same velocity also. Then there would be static friction between the two. But let's say before they acquire a common velocity. Before they acquire a common velocity, till that time, the velocity of the mass above will always be higher than the velocity of the mass below. Right? Right? Therefore, up to that instant of time, if the mass small m has got displaced by an amount, say delta x1, and the mass capital M has got displaced, say by an amount delta x2, then which will be higher? Delta x1 will be higher than delta x1. Why? Because at all times the velocity of the mass small m, upper mass, was higher than the velocity of the lower mass. So the delta x1 must have been higher than delta x2, right? So delta x1 must have been higher than delta x2. Now, let me calculate the total work done by friction. Work done by friction on the upper mass and work done by friction on the lower mass, right? What's the work done by friction? Total work done by friction on small m plus work done by friction on capital M. And realize that they are rubbing against each other. There is relative motion between the two masses, right? Work done by friction on lower mass would be minus Fk into delta x1. Fk is leftwards, delta x1 is rightwards, right? So minus Fk into delta x1. What's the work done by friction on the lower mass? On the lower mass, Fk is acting to the right, displacement is delta x to the right. So Fk into delta x2, right? That's the work done by friction, which you realize is, if I took minus Fk common, then this is like delta x1 minus delta x2. But delta x1 is larger than delta x2 because the upper mass at all times had a higher velocity compared to the lower mass. So this will be a negative number. So the total work done by friction in the event there is relative motion is always negative. If two masses are rubbing against each other, then the total work done by friction will always be negative. There is something cardinal about it. If they are rubbing against each other, then the total work done by friction ought to be negative for sure. That means the total change in kinetic energy on the two masses put together must be negative. That means delta Ke for the system, that means for the two masses put together must be negative. If the change in kinetic energy is negative, it means that the kinetic energy must be decreasing. The total kinetic energy of the system must be decreasing. So this means that the total kinetic energy must be decreasing, because change of kinetic energy negative, that means final kinetic energy less than initial kinetic energy. So kinetic energy must be decreasing. So if two masses rub against each other, the total energy gets dissipated, because the work done by frictional forces is negative, is always negative. Clear? Now, now, look, in a conservative field, let's say a particle is being acted upon only by forces of the field. Then work done by the field is always change of kinetic energy. Work energy theorem, if there is a conservative field, from work energy theorem, work done by the forces of the field is always change of kinetic energy. That's for any field, conservative or not. But in a conservative field, work done by the forces of the field is also negative of the change of potential energy, is also negative of the change of potential energy. Yes or no? That means in a conservative field, change in kinetic energy plus change in potential energy will always be 0. Change in kinetic energy plus change in potential energy must always be 0. So any change here must be at the expense of this, or vice versa. That means, this means change of kinetic energy plus potential energy must be 0. If the total energy is kinetic plus u, then change in kinetic plus potential is 0. That means there is never a change in kinetic plus potential. That means kinetic energy plus potential energy remains constant. That's the law of conservation of mechanical energy. That's the law of conservation of mechanical energy. Does it make sense to all of you? Huh?